All right. So we left off. I kind of was introducing that idea that if we could take 1,000 different samples, right, and then for each sample we calculate a sample mean, right? So we have like a column in Excel where I had like 1,000 different sample means. I could then kind of do a histogram or this relative frequency distribution to look at what the distribution of those sample means is. Now, it ends up being true as long as we have samples over size 30, is that these sample means will be normally distributed. And if I were to find the average or the mean of those sample means, it actually ends up being the exact same as whatever the population mean was from that data I sampled from. So think about if I'm doing this for like average income, right? I randomly select 50 people, calculate the sample mean. Randomly select another 50 people, calculate the sample mean. So maybe, the first time, maybe the true average is $50,000. Like that's the true population mean. But from my sample, maybe I see 45,000. So I saw, the first sample mean I saw was a little bit below the average of 50. Then the second sample mean I see, maybe it's a little bit above, and maybe I see, one that's a little bit further above, but then I take another one and I see something that's a little bit below, right? If I'm looking at 1,000 of these different sample means, well, yes, some of them will be to the left and some will be to the right because they might have had a few more people from the left or right end of the distribution in them. But once I have like 1,000 or a couple thousand of these sample means, well, some will be from the left side of the distribution, some will be on the right. So when I kind of take the average of all of them, the mean of those sample means ends up being whatever the original population mean was. You can go, there's a little bit more of a mathematical proof. If you're interested in looking up, I got it. Thanks. That you can look up, but I'll try to prove this to you today with some data. Okay. So the next, where did I put my I can get it out. So we can say that as long as we have a sample over 30, the sample means will be normally distributed. And even if we don't have a sample over 30, the mean of our sample means is always the population. What's also going to end up being true is that our variance for our sample means, right? So this was the idea that we've got these 1,000 different sample means in this Excel file. We can easily find the variance of those sample means as well. Now, what ends up being true is that the variance of my sample means is just the original variance of the data I sampled from divided by my sample size. So I'll give you a little bit of intuition why this is the case. Think about it this way. If I have my original variable of height, if I think about doing height, well, actually, we'll keep using income. So if I take this variable of income and maybe I have size samples of size 1. I'm only selecting one person, and then and it's kind of stupid because it's not, it's one observation, it's not a sample. But let's assume that we're just taking a sample of size 1. Well, then the variance, if I draw enough samples, it's just going to match up with the original variable itself. And this equation would tell me that, right? If I took samples of size 1, the variance of my sample means will just be the variation that exists in the data. Because I'm only looking at one person to calculate each sample mean. So I could draw a person at random. They make $300,000. So that's the sample mean I saw. I could draw someone at random. They only make $10,000. That's the sample mean I found. So I have a pretty wide range of values. But what if I take samples of size 100? Well, then I could happen to have someone in my sample who makes $300,000. But it's very, very unlikely everyone else in my sample makes $300,000, right? So these extremely high or low values kind of get averaged out over 100 people now. So my new variance, it's very unlikely I would ever see a sample mean be as high as $300,000 for averaging. It's very unlikely I'd ever see a sample mean as low as $10,000. So the variance on my sample means starts out at that original variance, but then just decreases as I take higher and higher samples. Right? As I take higher and higher samples, that denominator gets larger, and it's going to kind of reduce the range of possible values that I could even see. Does that make sense? Is that like why kind of taking a higher sample size would reduce the range of values I could see? You know, if I'm doing size 1, I could always, like if I do the height one, I could randomly select somebody who's, 7'2", and that's a sample mean now. But if I took samples of size 100, it's almost impossible for me to get a sample mean out of 100 people to be 7'2". Right? Those extreme values on either end, I'm just not going to see them for my sample means. So we've got the mean of my sample means, the population mean, and the variance of my sample means is just the original variance of the variable I'm sampling from over my sample size. And I talked about, how increasing my sample size will decrease that variance of my sample means. But then also, if there's just more original variance in the data, obviously that's going to increase the variance on my sample means as well. There's kind of two components there. So this should be pretty easy. If we want to do the square root, I want to bring this up at this point. If we want to do the standard deviation, it's just the square root of the variance, right? So I could just do square root of that variance there, the variance of my sample. I can rewrite that like this, and it's really the same thing, right? Because the square root of something squared is just itself, and then I'm just distributing that square root into the denominator. So we might start to see this written both ways, kind of depending on whether or not we have information on the variance of the standard deviation is going to dictate which one of these kind of formats is going to be most useful. Okay with this? Don't worry about this. I'll always give you examples where this is the case. It has to be such that we're concerned if we ever get samples that are too large relative to our population. So kind of what this is really saying is like we want to make sure that our sample is never more than 1/20th of the population. In practice, this is like not going to happen, right? Our populations are, if we're thinking about people, like 300 million, or talking about the world, we're talking about billions of people. So it's not likely that's ever going to be broken. There are some issues if this is the case. We won't dive into those subjects. So let's say I had this data set where I have all these births in Indiana from 2004 and a bunch of information on these births. I know that the original variable I'm sampling from, this birth weight, has an average of 3,287, or a mean of 3,287, and the variance, or the variation that exists in that variable is 360,000. If I wanted to find the mean of my sample means and the standard deviation of my sample means for samples of size 36, what would it be? Right? So if I was able to take, let's say we start out with this original variable x. The mean was what, 3,287, I think. And the variance was 360,000. Which I think what? That means the standard deviation would be the square root of that. That's 600. So that's my original variable I'm sampling from. What I want to determine is, what is the distribution of sample means of size 36 look like? Well, I know that as long as I'm over sample size 30, I said, we know that they're going to be normally distributed. And the mean of those sample means should just be whatever the mean of the variable I was sampling from was. I also know that the variance of my sample means is just going to be the original variance divided by my sample size. So this was right, my variance over my sample size. So I think if I do that, we get what, 10,000? However, I want the standard deviation. So that's going to be the square root of 10,000. So I guess beta. Does that make sense how you would work one out like this? Shouldn't be too bad. I mean, the mean of your sample means is always just the original mean of the data you sampled from. The only other thing we have to do there is just divide the old variance by whatever our sample size is. So if our standard deviation here was 100, if I ask you the same question, I won't use that for this, but it'll be a potential question that you might see something else. So let's say I want to size 100 now. So my sample sizes went up, right? So what should happen to the variance of my sample means, or the standard deviation of my sample means? It should go down, right? My sample size went from 36 to 100, so it went up. My denominator is larger, the whole fraction is going to be smaller. So if my old standard deviation was 100, I know the new standard deviation has to be less than that. So I know it's going to be one of these two, that's 60. And then from there, it doesn't matter what sample size I take, the mean of my sample means is always just whatever the original population is. So we should end up with, oops, I don't think I circled our answer here, but it should be C, right? Any questions on that one? Why that would be the case, or? So what is going on with this variant? We already talked about this, but like, just to kind of hammer this idea home. So this was the original variable, samples of size 5, samples of size 50. We said that as the variance goes down, right, what's going to happen to the shape of a normal distribution? Well, I think maybe the easier way sometimes to think about it is if the variance goes up, it's going to be more spread out, and so we get this flatter distribution. Well, here, as we take higher and higher sample sizes, the variance on our sample means is going to be going down, which means that there's less variation in the data. So it means that everything's going to be centered around that mean. We get a really, really peaked distribution. And you can kind of think about, well, I want to give a different way of thinking about this as well. So if we're taking higher samples, we know that the distribution of our sample means is getting more peaked, right? So let's say I've got this, and let's say the variance was 10. Well, let's actually just do 100. Then I know that the mean of my sample means is centered around the true population. So here, I could see, it's pretty likely I see values near the mean, but also values that are kind of far from the mean are also somewhat likely for me to see, or likely for me to observe. If I take, actually I should write here, this was the variance of my sample means. So let's say I take a higher sample, right? So that my variance falls, right? And it falls by quite a bit. So now I know my distribution is more peaked. So really what that's telling me is the sample mean values that are around the mean, and remember the mean is the true population mean of the data, the values that I'm seeing near the mean are going to be more likely for me to see, and it's going to be less likely I see sample mean values that are further from that true population mean. Remember, the whole point of what we're trying to do with a sample mean is have a metric that's reflective of the population. So if I start taking higher and higher samples, that's going to reduce the variance I see in my sample means, which is just guaranteeing that my sample mean is more likely or has a higher probability of seeing sample means close to whatever that true population mean is, even if I can't observe it. Right? I know that by taking this higher sample, I'm guaranteeing that it's more likely my sample mean is going to be a value that's very close to what that true population mean is. Right? Any questions on that? It's a little bit tough, and we'll kind of put more of a technical computational spin on this kind of next week, but this is the idea behind why we want to have these high sample sizes. We'll start to talk about confidence intervals, but this is kind of where it all starts. So you can kind of see here, I just had another thing where I went from like n is 1 to 50, and by the time I get to 50, notice it's almost, if the true mean was 50, it's almost impossible now for me to see sample means that are 30 or below or 70 or above, right? By taking this higher sample, I've kind of guaranteed that even if I'm only able to take one sample mean, the probability that that sample mean is something between 40 and 60 is very high, right? So I know that I'm not going to be too far off, even if I can only take one sample mean. So I want to try to give you a little bit of support. I think here I've got something before. Yeah, I got to talk about this. I've already mentioned this, but if we start with a variable that's normally distributed and then we sample from it, we actually don't need to have samples as high as 30 for the sample means to be normally distributed. If the original variable is normally distributed, then when we look at our sample means, they will always have a normal distribution. Now, if the original variable doesn't start out normally distributed, so maybe it's a uniform distribution, or maybe it's you've got some others that you can look at. It's like a hypergeometric distribution, like Poisson. Actually, yeah, we can actually even sample from a Poisson or a binomial. We'll kind of talk about that a little bit later on. But if it starts out and it's not normally distributed, I actually know that the sample means will still be normally distributed as long as I can get this sample size over 30. Right? So if the original variable is normally distributed, we don't have to worry about our sample size. But in order to know that those sample means will be normally distributed, we need to make sure we're at least taking samples over size 30. And I think, as we get kind of closer and closer, as we get higher and higher samples, we'll be getting closer and closer to a true normal distribution. It's going to be a little bit off kind of for lower sample sizes, but the higher the sample size we take, the more exact of a normal distribution. So that's the central limit theorem. Here's kind of a nice visual. I always sometimes steal things from textbooks, and I always really like this one. So that was a really good representation, and it would take me a lot longer to draw this. So notice if we had this original variable x, it doesn't matter how it's distributed, right? We've got a uniform here. I don't even know what the hell this is. We've got like a parabolic one here. We've got something that looks a little more like an exponential. Right? So no matter what the original variable starts off distributed as, notice that sample size 2, we already start to get some distributions that at least like these two are symmetric. I don't know if this is like a ghost looking thing, but we've got kind of symmetric, and these are still skewed a little bit. But then we get to size 6, and if we graph it with the distributions of these sample means look like, notice for some of these distributions, we've already kind of got some normally distributed variables. Now, these are getting close, but notice they're not symmetric. They're a little bit skewed still. What ends up being true is once we get to 30, no matter what variable we start out with, some of them are already going to be normally distributed at lower sample sizes. But no matter which of these distributions we started out sampling from, by the time we get to 30, our sample means will all be normally distributed. Right? Like I said, there's a mathematical proof of this, but we could just look at some data and prove it to ourselves. Now, if we prove things to ourselves with data, a lot of times these mathematical proofs hinge on the fact that we could look at an infinite number of things. So when we prove it to ourselves, we're always potentially going to be a little bit off because we can't get an infinite number of samples, but we can look at a very large number, right? So I had this Indiana birth data. It's about just under 90,000 observations. And for most of them, we have birth weight, we have the length of the pregnancy, so that's gestation period, the APGAR score, which is like a measure of infant health when they're born. And then we have whether or not the mother smoked. So this variable here is just going to be a 1, 0. So we looked at the means, right? I had this huge data set. I calculated the means and the variance just like it would in Excel. So you can kind of see our means for our 4 different variables and our standard deviations. So these are the original variables we're going to sample from. Okay? So, babies are pretty healthy on average and they're born in a hospital. This ends up being just under 9 months. And then this is the sad one, right? 18% of mothers use tobacco while pregnant in Indiana. So it was 2004, so hopefully it's went down a little bit, but not very comforting with the data. So what I then did was just graph out the distributions for each one of these variables. What ends up being pretty interesting is this biological measure of weight, for kind of birth weight when a child is born, is really, really close to almost a perfect normal distribution. So we got one variable that's starting out that we're sampling from that is normally distributed. So there we don't even have to really worry about the central limit theorem. We know the sample means if I say took a random sample of 100 births, and I did that 1,000 times, those sample means will end up being normally distributed as well. Now, the other variables didn't start out normally distributed. So length of the pregnancy, kind of a longer left tail, right? We see premature births, but not 12-month-old births. The health one, even more like kind of a left skew here, kind of a, notice this isn't even a continuous variable. This is actually discrete. It doesn't matter when we're thinking about the distribution of our sample means, right? Because for your sample mean, you can actually see a mean of 8.3 or 9.15. So even if the original variable is discrete, your sample means will still be continuous. Okay? And then I didn't draw it, right? The tobacco use one would just be a bar for 0.18, yes, or 1, and then 0.82, 0, right? They didn't smoke. So that one's definitely doesn't start out as a continuous variable. But when I calculate the proportion of mothers that smoke, I could see anything between 0 and 1, right? So there's an infinite number of possible values still there. So if we take a sample of size of 100, yeah, so I randomly select 100 births. I then calculated from that one sample of 100 births, mean birth weight, mean gestation, mean APGAR score, and mean maternal smoking. Right? I then did this 1,000 times. Right? So I had this data set of 1,000 different sample mean birth weights, 1,000 different sample mean gestation weeks, etc. Okay? From those 1,000 means, I could then start to find the mean of my sample means and calculate the variance of the sample means. Right? Once I had those stored in Excel, it's just 2 easy functions, right? Equals average, and then equals var dot would be var dot s. So I can actually calculate what those should be, which if I use those equations before, when I look at the mean of my sample means, those should match up with the original means of the variable I sampled from. And the standard deviation of my sample mean should be equal to the old standard deviation divided by the square root of my sample size. Well, here my sample size is 100, so the square root of my sample size would be 10. So all of these standard deviations of my sample mean should be the old standard deviations, we'll just move the decimal point, right? I'm dividing it by 10. Okay. So if I do look at these, right, I actually did this and calculated what the new one should be. Now they're a little bit off because I only have 1,000 instead of an infinite number of sample means to determine this from. But it kind of gets the idea, or the idea across. So if I looked at the mean of my sample means, the birth weight, it's only 1 gram off, right? It's actually less than that because I rounded these to integers. It was actually even closer. But notice I'm getting pretty close, even at only sample means, or even when I only have 1,000 sample means. Right? If I did like 10,000, I'd be even more exact. Right? Length of the pregnancy, we're only off the second decimal. Here, we match it up perfectly. Here, we actually match it. I say match up perfectly. It was off like the 4th or 5th decimal, but we got really close. When I then look at the standard deviations, they should be the old standard deviations divided by 10. Sure enough, 600 divided by 10 is 60. 2.66 divided by 10, I should have 0.266. This one I rounded the second decimal, so it wasn't exact, but they were close. And kind of same kind of idea here. Honestly, the only real reason they look like they're somewhat different from each other is because I was rounding at that second decimal. But we actually, we can prove this to ourselves. In Excel, there's a random number generator, so you can generate random numbers and then select those observations out of the data set. So I literally had 1,000 different samples built, and then I calculated these means, and then calculated sample means, and then calculated the mean of those sample means, and then determine the standard deviation as well. So these are kind of proving to ourselves that these things will hold. The mean of my sample means is the mean of the original data I sampled from, and the variance of my sample means will just be equal to the old variance of the data I sampled from over divided by my sample size. Okay. Any questions on this? Like I said, you can look at the mathematical proofs and see like at what point is it a close enough approximation, and it really is at a sample size of 30. Right? So the first 2 things I told you looked like they held here, but what I could also do with those 1,000 sample means is do histograms for each one. Look at the distribution. Now, 100, that sample size is way over 30, so they should all be normally distributed, right? So if I look at birth weight, right, and I looked at my sample means, and I did my histogram here. I mean, this is like a perfect normal distribution. Notice, because I'm taking samples of size 100, I know the variance will be smaller than the original variable, but you can also even just look at the range. I'm only seeing sample means between what, 3,500 and 3,050. If I go back to the original variable, I was seeing really low birth weights for these premature births. I was seeing some births in the closer to 5,000. But when I take the sample size 100, those extreme values kind of get averaged out, right? So I'm looking at the distribution of my sample means. I can get there. It's going to be a much narrower range of values, right? Because it's kind of ensuring that I'm seeing a sample mean that's going to be closer to whatever that true population mean is. I then can look at the other variables, like gestation. I mean, almost a perfect normal distribution. The APGAR score, maybe a little bit off still, right? But a pretty close approximation to a normally distributed variable. And then if I look at maternal smoking, that was the one that I started out with just a 1-0 variable. When I'm looking at those sample means, there's a little bit of something goofy here. It's probably because I had to choose cutoffs to put these in bins, but pretty close to a normal distribution as well. Right? And if I were to take more than 1,000 sample means, these would look a little bit better. And if I could, do even like 10,000, they would start to look a little bit more clean. Okay. Any questions on it? Not too bad yet. So told you about all those other distributions, and now with the sample means it doesn't matter. Right? As long as that central limit theorem is met, as long as we have sample sizes over 30, we know the sample means we normally distribute. It doesn't matter what the original variable started out as. Okay. Anybody know who this is? I like you. So you should all watch this movie. This is hilarious. It's a classic, and if you haven't seen it, you're doing yourself a service. That's my work for the day. So what we want to do is, now that we know our sample means are normally distributed, we can start to think about, well, I can actually determine how likely or unlikely it is I see certain values for these sample means. Right? So the first question I'll ask is, does my central limit theorem apply? So do I have a sample size over 30? Okay. If it does, I know my sample means will be normally distributed, and that mean of my sample means is the mean of the original variable I sampled from. I then can think about, okay, if I'm interested in a certain value, so if I'm interested in a certain sample mean value, well, because I know this is normally distributed, the distribution of my sample means is normally distributed, I can turn that value into a z-score, right? How would I do that? Well, remember before, this was the equation that we were using for our z-score. Well, now I'm going to do the same thing. It's just I'm creating a z-score for the statistic I'm interested in. So instead of just the original variable x, I'm looking at z-scores for sample means. So I'm going to take a sample mean cutoff value, subtract the mean of my sample means, and divide by the standard deviation of my sample means. Right? So the way that we calculate z-scores is always the same method. I subtract the mean of the statistic I'm looking at. It's just now it's not an original variable, it's sample means. And I divide it by the standard deviation of the statistic I'm looking at. Now, from here, I know that the mean of my sample means is simply the original population mean, the data I sampled from. And the standard deviation I can plug in, well, that's just the square root of the original variance over my sample size. Right? So my new kind of z-score equation is going to look something like this. Now I can rearrange the denominator a little bit, and notice I put the square root there. Either way, I'm really writing the same thing. It just depends on what information I have. If I have the variance or the standard deviation of the original variable I sampled. Once I have this z-score, it's just like what we were doing before, right? Once I have the z-score, I can tell you the probability that I see that sample mean value or anything below it. Because once I have a z-score, just look it up in the table, right? And then sometimes if we wanted to, the probability of saying that or greater, maybe we have to do 1 minus, or we're looking for the probability in between. But once we get to step 2 and we calculated the z-score, it looks like exactly like what we were doing before, right? We're just kind of dealing with a normal distributed variable. Questions on this? Look up the probabilities. There's that fifth step, right? Sometimes we have to subtract from 1 if we want to the right. I think we'll work through the example now. So let's say, we'll kind of doesn't really have much of a context, but just actually working through one with some numerical values. So I've got this normally distributed variable. It's got a mean of 5. So I'm starting out, I'm sampling from this original variable, and I know it has a mean of 5 and a variance of 2,500. What I'm then going to do is think about, okay, with that information, if I take samples of size 100, what will the distribution of my sample means look like? So the distribution of my sample means, well, the mean of my sample means should just be whatever the original population mean was from the data I sampled. Also, this is kind of, I don't know why it does this on my computer. I'm using this online, but there's some reason the transitions over. This is sample mean, kind of the bar gets lost, right? But what we eventually want is a probability to see a sample mean between 10 and 15. So that's why I was kind of determining what the distribution for my sample means would look like. So now I think about what region am I looking for? I want the probability I'm in between 10 and 15. I also know that the variance of my sample means will just be the original variance divided by my sample size. So another thing that might be easy is, or might make it easier moving forward, is just find the standard deviation of your sample means right away, which is the square root of the variance. So here we would end up with 5. Now this is going to look very similar to a problem that we actually have already worked through, because now that I know I have a normal distribution for my sample means, right, I can turn these two values into z-scores. How am I going to do that? Well, if I look over here, right, I'll take my sample mean value I'm interested in. So for that first one, it would be what? 10 minus the mean of my sample means, which I have over there is 5, and the standard deviation of my sample means is what I'm dividing by. So put this in my calculator, or I can just think about that value was 5 away from that mean, and my standard deviation was 5, so I was 1 standard deviation away, or I end up with a z-score of 1. I can then plug in 15, right, for my second value I'm interested in. 15 is 10 away from the mean. My standard deviation is 5. 10 would be 2 standard deviations. Or if I go ahead and plug the values into that formula, I get my z values of 1 and 2. Now it's just a matter of looking those up on the table, finding the probability I see a z-score of 1 or less, and then subtract that from the probability that I see a z-score of 2 or less. Okay. So we kind of walked through, found our 2 z values, go to the table. I want 1 and 2 are my z values, so 1.00, 0.8413, and then go down to my 2.00, 0.9772. So now that I have those 2 probabilities, there we go. It's just a matter of taking the difference between the 2. Right? So once we got to the z-score part of this, it's literally a problem that we've already worked through in class, right? The process is no different, right? Once we get to those z-scores. Any questions? I know I'm going a little bit quicker through this stuff. Okay with this? So what if we wanted to do this one? So I've got, actually I'll have you guys work. Well, we'll talk about it. So I've got this length of the pregnancy or gestation weeks, and the population mean is 39, the population variance, population mean is 39, population variance is 9. If I take a sample of 81 infants, what's the probability that the sample mean I see will be 39.5 or greater? So let's just start thinking about what we've got. So I'm interested in a value for the sample mean. I know the mean of my sample means will be whatever the original population mean was. So the data that I'm sampling from is this gestation weeks, and the population mean is 39. So I know the mean of my sample means it should be centered around that same value. If I want the variance of my sample mean, I know that's just going to be the variance of the data I sampled from over my sample size. So the variance of the data I sampled from was 9, sample size was 81. I wanted the standard deviation here. Excuse me, I think this ends up being what, 1/9. So the square root of 1/9, or I have a standard deviation of 1/3. And I don't have to do this ahead of time. Like, if I wanted to, I could plug everything in to my denominator. But I want to remember that this denominator really represents the standard deviation of my sample means. So I can either plug everything into the denominator of this equation, or I can kind of calculate it ahead of time, do the intermediate step, and then plug it into that. There's really two ways of, two forms of this equation. Okay? So if I want to break it down to another step, I can do that. So what I wanted was the probability that I see a sample mean of 39.5 or greater. So right away, I know this probability has to be less than what value? Yeah, the area to the right of the mean is 0.5. I'm looking at a value that's above the mean, so that area to the right of that will be something smaller than 0.5. From there, how many standard deviations away am I? Well, I can actually plug these values into my z-score equation and come up with that exact z-score. But if I'm just looking at this here, I'm what, 0.5 away from the mean? So it looks like I'm really close. But if I look at my standard deviation is only 0.33. So I'm actually like approximately 1.5 standard deviations away. Now, it's not the exact value of z-score, but I'm just kind of giving a raw kind of idea. It's around 1.5. So I'm almost 1.5 standard deviations away from the mean. So if I was guessing, 1.5 standard deviations isn't super close, more than a standard deviation away, my probability is probably going to be a little bit closer to 0 than it would be to 0.5. So if I'm looking at A or D here, those are the only possible answers because they're the only ones less than 0.5. But we said being 1.5 standard deviations away, it's probably going to be a little bit closer to 0, my probability than it would be 0.5. So I probably would guess A here. Sure enough, we plug in our values, right? So the sample mean I'm interested in is 39.5. The mean of my sample mean, so that original population mean is 39. And then we calculate that standard deviation of my sample means, which was 1/3. So 1/2 divided by 1/3. Actually, it is 3/2. I should have known that. So when I was saying approximately 1.5, it actually is 1.5. For some reason I was thinking 0.3 there, but it's 0.3. So we end up with this z-score of 1.5. We looked that up in the table, right? I think if we do that, the table will give us that value. And I'm not going to look it up every single time. Hopefully we're starting to get comfortable finding that z-score and looking at the probability in the table. So we find about 0.9332. Remember, we originally wanted the probability of seeing that value or greater. So we have one more step, which is subtracting it from 1. So final step, subtract that from 1. and we get that probability is quite a bit closer to 0.0668. Any questions over any of the steps? Going okay with this? It's not too terribly different from what we were doing before. Just kind of this added wrinkle where to determine the standard deviation of the statistic we're interested in now, you have to divide by the samples. I'll introduce this today. It's not too terribly different from what we've been doing. So all of this stuff that I said holds for the sample mean would also hold for the sample proportion. And we've kind of actually already looked at a sample proportion already, even though I was kind of referencing it as a mean. So when I was looking at that maternal smoking variable, the only values I could see were between 0 and 1. Right? The proportion of mothers that smoke while pregnant, if every mother smoked, it would be 1. If no mother smoked, it would be 0. Right? So I was seeing from my samples any value in between 0 and 1. Right? So that would actually represent not a sample mean, but a sample proportion, because the original variable could only take on 2 values, 0 or 1. Right? So if we go back and remember with our binomial, this is kind of what we were looking at there, success, failure. Well, the mean of my binomial distribution was n times p, and the variance of my binomial distribution was n times p times 1 minus p. So you can think about now, if I'm not looking for the number of successes, but rather the proportion of successes, well, if the average number of successes is n times p, right, then the proportion of successes would be, well, the number of successes divided by the number of trials, which we're just left with p. Right? So when we're thinking about the mean of my sample proportions, right, it's just whatever the original population proportion was. And the variance of these proportions will simply be same kind of idea. We divide by n, because that represents the variance on the number of successes. We want the variance on the proportion. So it just becomes p times 1 minus p, right? Dividing both of these by n. Okay. Now, we can rewrite this in slightly different, sorry. That's the, I didn't want to do this. The variance on my proportions, right, is just dividing by n. But then if I want the variance of my sample proportions, I have to take the variance just on the general population proportion and divide it by n again. So the first time I divided by n, that was just because I was turning the number of successes into proportions. And then from there, when I'm looking at my sample proportions, it's just like with the sample mean. I'll take the variance of the variable I'm sampling from before the variance we have was just this, right? Just whatever we calculate the variance to be. For a proportion, we know the variance of a proportion will be equal to p times 1 minus p. So if you want to think about it this way, right, these are really saying the same thing. So the variance of my sample proportions is simply going to be the variance on the population proportion, which we know will follow this formula, p times 1 minus p. And then just divided by my sample size. Same kind of idea with the sample mean. As I take greater and greater sample sizes, I'm driving that variance down to 0. If I only take samples of size 1, I might select a mother that smokes while pregnant. I'd have a sample proportion of 1. If I start taking samples of size 100, I'm not going to see 100 out of 100 mothers smoke while pregnant as my sample proportion. Okay. So it's kind of a similar idea as what we were doing with our sample mean over there. Once we know that this is going to be the case, so as long as we got sample sizes over 30, we can think about, well, what's the distribution of my sample proportions look like? So what's going to be true is, as long as I have sample sizes over 30, my sample proportions will be normally distributed. The mean of my sample proportions will be whatever the original population proportion of the data I'm sampling from was. And the variance will be equal to, we said, the variance of my original variable, or original proportion variable, divided by my sample size. So I could then start to do things like, okay, if I've got a coin, I'm flipping a coin, right? Got 100 coin flips. What's the probability I see 55 or more come up heads? Well, I know that the population proportion for a coin flip example is kind of easy. That should just be what? Yeah, 50% or a proportion of 0.5. So the probability that I see 55 or more, well, I'm looking at proportions. So I'm not looking for 55. I'm actually thinking about 0.55. Now from here, I could turn this value into a z-score. We haven't moved that equation yet. But we can kind of probably come up with it on our own. Notice before, to turn the sample mean into a z-score, I just take the value I'm interested in, subtract the mean of that statistic, divide by the standard deviation. If I want to turn a sample proportion value, here I was interested in the sample proportion of 0.55, I'll take the statistic I'm interested in, subtract the mean of that statistic, divide by the standard deviation of that statistic. Well, here, I know the mean of my sample proportions is just whatever the true population proportion is. And then the standard deviation, well, here I've got the variance of my sample proportion. So the square root of p times 1 minus p divided by n. So I'm just plugging in the things I know. That z-score always follows the same format. It's just that for different statistics, the standard deviations might be a little bit different in the way we calculate them. But now from here, once I have a z-score, everything plays out the exact same way. So here I would take that 0.55, plug it in. 0.5, plug it in, plug it in here, plug it in here. My sample is size 100, so plug in 100, that sample size. That gives me my z-score. I get a z-score of 1. We know how to look it up in the table. Once I look it up in the table, that gives me the area to the left. I wanted to probably see 55 or more, so I have one more step, which would be subtract that from 1. So these are really it's really the same process. The only difference here now is our z-score takes on a slightly different format when we're looking at proportions. And it's kind of tough to think about because it's like, are the sample proportions truly continuous? Because I can't, out of 100 coin flips, I can't actually see every single value, right? Because 1 out of 100 is 0.01, 2 out of 100 is 0.02. So I do have some gaps in my distribution. But that's so it's a close approximation for what that probability is. So there are going to be these gaps, but we can still think about it as continuous. And one of the main reasons why is if I start to take samples of different sizes, think about the values I could see for my sample proportion do range between any value between 0 and 1, right? So as I take different sample sizes, I could see sample proportions not of just 0.01, 0.02, but I could see 0.013597 if I had the right sample size kind of chosen. So even though when I'm thinking about one specific number of for n, my sample size, if the sample size can change, I really could see any value for my sample proportion in between 0 and 1. And that's why it still works. That's why we still treat it as a continuous. So we'll work on some more sample proportion examples on Monday. We'll then transition to thinking about confidence intervals, which exploit a lot of the principles we've been talking about with our sample mean and our sample proportion. So a lot more computation, a lot more use of those tables, z-tables next week. And I'll probably do a little bit more stuff in Excel. But stuff we do in Excel won't apply to the current individual assignment, right? We've already kind of worked through all of that. Yeah. Any other questions for me before we get out of here? All right. Enjoy your weekend, and I will see you guys on